Okay, if you recall that we were doing something here last time. Okay, we modeled the things, quite please. We modeled the things last time. Okay, and we were like kind of close to answering the question that, well, why the ozone level, what is the ozone levels could be, and why and how. Okay, but then when we came to the level that we went to the field and we were trying that to say if the atmosphere behaves the way we thought the model should, and we had concluded that the model really failed. The simple reason was the ozone levels were much higher than what the model predicted. Okay, and that's where I had left you to think as to where the problem that is going on. So we looked if you recall what I had said was that we can't really look just the little box the way I was trying to model. The box should be a true atmosphere. Okay, we just can't put NO in there, NO2 in there, and let the sunlight come through that one and hope, well, the ozone will be formed. And ozone is formed, no doubt about that. But we have to look, the atmosphere, I said, is a very complex thing. There are thousands of reactions, okay, occurring at one time, competing with each other, being decided as to who will be formed and who will be surging ahead and who will be falling behind and things like that. So what we will do in this class is that go to some other reactions that might be occurring in the atmosphere, and then try to answer to some extent that where and how ozone could be a little bit larger. Okay, so that is where I want to go from last class, and then we'll go to lecture 8 and the slide show. So we had seen the importance of the OH radical, okay, and now at least simplest thing, carbon monoxide will certainly be in the atmosphere. Okay, so let's see, apart from the OH radical that was formed, what it can do to CO for that matter. CO is generally very unreactive gas. We all know that. Okay, it does not even react with the moisture. It doesn't react. It really needs very high temperature, and that's for like even when we are talking that we are inhaling CO, CO does not react anyway. CO goes all the way to the lungs and gets transferred into the bloodstream, right? We all know that. Whereas, for example, the ozone is so highly reactive, it doesn't reach as deep in the lungs. Okay, it reacts and whatever effect it needs to do, it does in the upper respiratory part. Okay, but here even CO is affected by the OH radicals, and you see that it can form with CO2. Okay, and it can also give rise to atomic hydrogen, and atomic hydrogen can be very, very reactive and form HO2. Okay, I know you have heard about H2O, but in this course also understand what is HO2. And HO2 is very, very fundamentally important radical in the atmospheric chemistry. Okay, so we'll talk more about HO2, but just think that HO2 can be formed by what is this simple reaction. Very quickly, somebody tell me how we had formed the OH, so that we know that we are still. Quickly tell me, how was the OH formed? What is the route for the OH formation? Well, because we did discuss yesterday that OH is formed. NO reacting? Huh? NO react with water? No. Please tell me. Look into the things. So you should take some broad notes at least, and tell me where did the OH come from? Because you see, we don't know what was happening with ozone breaking down. Did we discuss the ozone breakdown? It forms the nascent oxygen. Nascent oxygen can be in two forms, ground state and excited states. Ground state can react with oxygen, can give me back ozone, and if it is excited state, it cannot react with oxygen, we said, or did we not say that? Did we say that or did we not say that? If we don't, if I say, then I want to do it again, but if I had done that, then I don't want to do it again. Tell me, I mean, do you recall that what I am saying, or you don't recall it? I think we did. We did, right? Or you wanted to do it again? Yeah, we did a lot. We in fact we did in details.
The oxygen molecule of excited state react with water and form OH.
So you can written down.
So you have given ozone fertilizes on ozone plus
Ozone photolyzes, and it can photolyze depending on the UV radiation. The photolysis of ozone is in two parts. The two pathways are there. In one way, it can make the oxygen which is at the ground state, right? And that ground state oxygen can react again with oxygen to give me back ozone, right? So that is a more of null process. Nothing has happened really. Okay. The other route is, depending on the UV radiation wavelength, it can produce atomic oxygen which is in the excited state. That cannot react with oxygen to give me back the ozone. Rather, that O, which was 1D if you recall, the way we had mentioned, right, that can react only with, or that can react with many things, but it also likely to react with water. Okay. So O, which is in excited state, plus H2O will give me what? Twice OH. And that's where the fundamental thing that I got OH. Okay. So don't forget last class what we discussed. Okay. Because the whole thing, photochemistry revolves around OH radical. Okay. It's very, very fundamental thing. Okay. So don't forget that we had OH, and then now the new thing which we are talking is the formation of HO2 radical, that is a hydroperoxyl radical. Okay. And now the interesting part is you can summarize these two equations in simple form: C plus OH radical, plenty of oxygen, CO2 and HO2. And this HO2 is capable, and rather hugely capable, of oxidizing your NO to NO2. Okay. Just see that, well, there are some more people, okay, other than the OH, I beg your pardon, other than the ozone, to oxidize NO into NO2. Okay. Last time when I gave you the reaction, we only said the thing which can oxidize NO to NO2 was ozone, right? You remember that? And but there are the other routes also. So in a way, what I am saying is, only we are starting with CO, and then there is additional source through which I can produce NO2. Okay. So in a way, what is happening is, it's not only the ozone, but I am able to put more NO2 in the system. Okay. Recall? So partly it will answer, if you have the more NO2, the only way through the ozone in troposphere can be formed is by dissociation of NO2. Right? I repeated it again and again. Okay. So if I am having excess of NO2, obviously, which I had not considered CO in my earlier model, for example, so my model failed. Okay. Now here I am saying, well, there is something more going on than the little box that we considered last time, and there in the box we had only put NO, NO2 and somewhat little initial ozone concentration, and then said, well, we should get the things, but it didn't happen the way it should. So you see, already there is an additional pathway, okay, of forming the NO2 just by considering little amount of CO. Okay, and then again everything triggered by OH radical. Don't forget that the OH radical is so critical. And now you should not forget, where did the OH radical come from. Okay. All right, and then the funny part is regenerated. I have available for more of producing HO2 and more of conversion because OH is back. Okay. although OH is so reactive that the concentration in the atmosphere is very, very small, and I told you that the amount of the concentration was in some molecules like 10 to the power 11 molecules per liter per meter cube. Okay. We also said that, well, if you have plenty and plenty of NO2 being formed, much faster than it can be consumed by ozone, okay, there is a terminal reaction that the NO2 come out of the system. Okay, there has to be sink for everything. So what we are saying here is that you had the NO2, excess of NO2, you also had the OH radical, it can convert to H1O3, and this is one of the routes for the forming the acid and removal of NO2 from system, because this reaction cannot go back. Okay, so there is also a removal mechanism for NO2 from the atmosphere. Okay. So this is the little summary of the things of reactions. That is what so far we have done. You recall this equation, you recall this, okay, you recall this, you recall the excited state giving you the O, which that O can react with water and form the 2OH radical. That's what just now I said. Now this OH radical, okay, now there are additional things. OH radical can convert CO2 and form the HO2. HO2 what? HO2 was what? Hydroperoxy radical. Okay, and then this HO2 can now is able to oxidize NO, just not the ozone. Okay, so this can also oxidize to produce NO2. Okay, OH is regenerated, and there is also reasonably good possibility that if you have more and more NO2, then it can be consumed by the ozone, and then you have the OH radical, it can go into the terminal stage and get out of the process. The NO2 that gets out of the process and form the HNO3. What happens to HNO3 we'll see it a little later, but they are the rate constants, and the way we write the equations, okay, the model, we can also write the model for this one. Okay, clear? This gives pretty much the summary of what all we did. Okay, let's recap. The basic reaction mechanism for the CO NOx system exhibit many of the key features of those involving much more complex organic molecules. Okay, we just consider a very simple thing. In particular, the role of OH as the oxidizing species and the NO to NO2 conversion by HO2 are central to virtually every atmospheric organic NOx mechanism. So this, I give you one example, and we'll give you more examples that, well, there are many more ways through which you generate HO2. So if you are able to generate HO2, it means you are able to oxidize NO much faster to NO2. If NO2 is formed, you are forming ozone all the time. So see how there is a little turnaround in our model, and then we can say, well, how the more ozone should be formed in the atmosphere, just not by the simple models. It is useful to proceed to a molecule that is somewhat more complicated than CO, and let's see what happens. So there is another example of the atmospheric chemistry coming up with the formaldehyde. Okay. Formaldehyde is very important pollutant. Okay, it is directly emitted from the automobiles and from the combustion processes. Okay, largely from petrol driven vehicles. Okay, maybe we'll see why SCHO comes from the petrol driven vehicles. Okay, and then this SCHO is again pretty reactive. Okay. Okay, the formaldehyde SCHO is a primary pollutant, and also to some extent the secondary pollutants formed in the atmosphere. These are basically emitted from the automobiles. Formaldehyde undergoes two routes. Okay, for the primary reactions in the atmosphere. One is photolysis and another is the ordinary chemistry. Okay, so let's see the two routes. SCHO, again the H nu that we are getting onto the earth, the wavelength which are reaching on the earth, can break it down to the atomic hydrogen and then formal radical, and this atomic hydrogen can react with the oxygen present and give me the HO2, more HO2. Okay, more HO2, and then this SCHO that can also combine with oxygen to give me more HO2. Okay, so this is another thing, and then another reaction which can happen is this route. it can go out of the system also by hydrogen, combining with the hydrogen to produce the hydrogen. Okay, and this you see here, this can go this way or this can go this way. Okay, this is a summary of this, but this is the ordinary reaction that we are talking about, that it can also form the hydrogen NCO, and the things are happening competitively. Okay, it's not that, well, this is happening, this is not happening, and that is all will be decided by what? Which will happen faster, which will happen slower. And also the rate constants and things like that. That particularly governs, dC by dt is depends the concentration, initial concentration, and the rate constant. How quickly the things will change, who will become first, who will be more, who will be less. Don't forget the importance of the rate constant. Okay, so this is the two route. So again we have we took the example of CO, we gave another example of SCO, and again what we get is HO2. Okay, and once we are getting HO2, okay, again we are getting HO2, you are again forming the HO2. What is this route 2 business, if you really see, is the overall, that's what we are getting. What are we getting overall? That is what we are getting. Okay, go back to the previous reactions. And the route 2, it can also form the HO2, CO and H2O. So in summary, what we want to say is that all reactions are because of the photochemistry, and reactions with OH radical, SCHO, HCCO, and it will give to HO2. What is SC means here? Hydrocarbons. Okay. So in general, broadly speaking, the hydrocarbon will also give me the HO2. If we have the HO2, will form NO2 and NOx removal from the system. That can also happen, and we should add here the NO2 can also give rise to ozone. The only route of forming the ozone, I repeat again and again, in the atmosphere or in the troposphere, largely the troposphere, is by the breaking down of NO2. Okay. Okay, let's summarize these reactions. All the reactions involved in CO NOx chemistry are summarized here. Well, that is fine. That is a repetition. That is a repetition. That is a repetition. This SCHO, if you remember, it was formed the HO2, sorry, and then it can also terminate in the form of the hydrogen and carbon monoxide, and then this is another reaction. So you get HO2. HO2 can plus NO will give you NO2, regenerates OH radical, and this is the terminal reaction. Writing the same thing what we had discussed, but in addition to writing the thing, we are also writing the rate constant. And this, when I am referring to table 4.2, please see Sinfield. Okay, please see the Sinfield if you really need to look at that. Okay, because these things were given in the first lectures we are given that, but this thing is more or less scanned, and again remember the units of the K can be very different. Okay, now let's model the whole thing as we did last time. You remember the model that we prepared was this one, K1 upon K3 NO2 upon NO, that we had done in the last class. And now if I have to write the steady state equation for the which system, for CON, COH reaction, and also involving SCHO, right, SCHO. So what you see here at steady state, of course, don't forget that, you have to write the reaction, put dC by dt equal to 0 and all, and run through some algebra and things like that, and you can find out the OH steady state concentration will depend on the reaction 4 and reaction 7, and the reaction 4 and 7, you can see that, well, that is how you will get the, you can derive it. I mean, it's more of algebra at steady state, don't forget that. And then you can find out what is the steady state concentration of HO2 ions, okay, in the atmosphere. that will involve the rate constant of certain reactions, it will involve SCHO, it will require the NO and that sort of thing. We can also write our equation in terms of variability as a function of how the DNO2 now, don't forget now the DNO2 should involve the SCHO, and this how the NO will change, how the SCHO will change and things like that. Mostly these are the algebra that you need to do. Okay. Now you are a little familiarized with this one. In the next class maybe we will give you one assignment. There's something involved because seeing is one thing and doing is the another thing. So that if you do run through the exam that assignment, so you are able to familiarize. And now if we see, if you are able to write, okay. Now what we are trying to do now is, first thing yesterday what we did was we took the box and something like ozone. We are making it a little complicated. We are having the box and I can model it, and I have modeled it here, and see the results of the model which we should try to understand. Okay. I will explain you what are the things, but first of all see, if we took the initial concentration NO2 as 0.1, NO as 0.01, very small quantity comparatively. Okay. SCHO is 0.1. Okay. Let's take this example, and then we solve the things, and then what happens is, before SCHO can do something, okay, the first reaction that we were talking about of this kind, okay, they resettles quickly, their equilibrium settles quickly. Okay. So there, when this equilibrium settles quickly in the movement, what is happening to NO here, converted to NO2. Okay. So what will happen? Let me see, where is NO? You see here NO.
Second one, yes.
Where is this is NO, right? Okay. You see here NO. What is happening to NO? Okay. You had the NO2 and then the NO. Okay. What happens that NO2 and the NO is little bit increases. Okay. Why? Because you see here the ozone is formed quickly, and this ozone, which we had no ozone, this ozone, first of all, immediately what happens is that NO2 is attacked. Okay. And NO2 quickly reduces, because NO2 will quickly, the first thing will happen will be to NO2, because we have NO2 in the system. Okay. And what will happen to, we have started, NO was less. How much was the NO2 and how much is the NO? NO2 is much higher, 0.1, and this is only 0.01. Pay attention, because this will require some attention. So I have lots of excess of NO2. What will happen quickly, within seconds? NO plus O, right? And so I already had some NO, 0 plus this NO. What will happen instantly? NO level will rise. You started NO with 0.01 somewhere here, and within seconds it went to 0.045. So it just takes off from here, shoots at 0.04. Okay. Clear? Okay. And we have the reason that why it should be. So it goes up. All happening in few seconds. In a few seconds. Okay. Then you will see that ozone is formed. Okay. Then you will see that ozone also picking up from 0. Okay. quickly going to some level within very short time, okay, and it will change rapidly, okay, that is what is the thing. Then what will happen once I have gone high on NO and I also am going high on ozone now? What will happen to NO? NO should go down eventually. Peaks immediately and then NO goes down. Okay. What will happen to NO2? Why should it decrease? How can both decrease? See, how can both NO2 and NO both are decreasing? Is that right? See in the picture. Are they both decreasing? Okay. Ozone is going up. That's fine, right? More and more ozone is formed. That is okay. Okay. Any clue, or can you find clue from here? Converted into HNO3. You see, the thing is, all things are happening. Now what you are getting is you are forming more and more NO2 now. Okay. After this you have the ozone NO, but then and already NO2 is pretty high. Was the NO2 high that I started with? Was it high in the relative sense, right? And then don't forget that I also have the additional mechanism now in place for converting NO into NO2. What is that additional mechanism I am talking about? What is that additional mechanism that I am talking about that is converting NO into NO2 other than ozone? HO2. And where the HO2 has come from? Where has it come from? Because I have put in the system formaldehyde. Okay. I have changed the things here. I am not talking the same box. I am talking about the different box. Okay. So I have more and more conversion of NO2, and then if I have the higher NO2 conversion is higher, okay, it can, the two things can happen. If NO2 is going up, it can either increase O3, yes, certainly possible, but then I should also not forget from my chemistry is that if I have this OH and also high amount of NO2, it can take this NO2 out of the system and form HNO3. Okay. So as a result, NO2 is also being removed. It means the rate of removal of NO2 is much faster than the rate of removal, rate of formation of NO2. Okay. And if the rate of removal of NO2 is faster, what will happen to my ozone concentration after some time? NO2 is being taken out. My formation of ozone will tend to stabilize, because every time I want to make more and more NO2, more and more ozone, I should have more and more NO2, but unfortunately my NO2 is decreasing, right? So at some point ozone, the way it started, okay, with time it will tend to stabilize or maybe even come down or make some kind of steady state, which it is reaching at steady state. Okay. So we again use another model, and this time at least the model results we are able to explain and how the things are happening. Okay. Now question for you. Okay. If suppose I was also measuring here HNO3, what will happen? It will increase. Okay. It will increase. Start from 0, maybe it won't pick up so much here, and then it will pick up something and it will pick up more, because of NO2 is decreasing, NO is decreasing, ozone is stabilizing. So it means I am going towards more of removal of that thing. Okay. This is how we all the time, and we should use the models because we understand the mathematics, we can solve the equations, and we should be able to say as to how and why the behavior will be the way it is. And then the science, we are not, whatever the science we are learning, the science is not for learning and passing the exams, science and learning that eventually we want to apply this understanding to solve the problems. Okay. Then solve the problems of ozone formation. Okay. Somebody might be interested in reducing the HNO3 formation if that is the issue, because it's not that we just read it and put it in, because the models are done, the science studies, people publish the things, but then somebody should be able to use that one. Okay. Now quickly tell me if you if you are a little excited with what I said, what is that you learned if I want to reduce my ozone formation, what should I do? Control the hydrocarbon SCHO emissions from the car. Okay, all agrees? Okay, sounds very funny, but then what I can say is that, well, if I could control the hydrocarbon emissions from the car, my ozone levels will come down, right? And my chemistry says, my science says, and my model says. Okay, so ozone, otherwise ozone I can't control in the atmosphere. Okay, so what I can control, either control NO or NO2, okay, which again will not be very easy for me to control NO, NO2, but what I can do, I can improve my combustion, okay, and try hard, okay, and then I can improve my combustion, so my SCHO emissions, okay, will reduce, and hopefully that reduction will result in reduction in ozone concentration. So we all take the decisions based on the science for our better things. So I just don't think it's just the class we do and we learn something, and like, and people indeed uses this knowledge. Okay, well, case 2. Okay, what is happening here? Initial NO concentration increased, very high NO concentration. So here what you will see here, if my NO is high, okay, this of course will break. If my NO is high, then my NO, the conversion of NO to NO2 will be very quick, okay, and my NO will quickly, there is no reaction required, but in fact slightly the NO2 will go up, and then it tends to start decreasing. Okay, and you see here the NO2 may peak, because that time this was overwhelming reaction, but this time I have the NO is large. Okay, see the difference. That time I was dealing with small NO, that was like 0.01 something, now I have the high NO. So now, then if I have a high NO, okay, and then therefore as you have some oxidizing thing, this NO will be quickly going into the NO2, and then once you have the NO2 will decrease by 2 routes. One is forming to HNO3 and one is breaking down towards to form the ozone. So ozone goes up constantly, NO constantly coming down, okay, that we can see here, and then finally SCHO will constantly go down. SCHO has to go down. I mean, this is no other way that can go. So here, because I have the high NO already in place, okay, let's not forget that I have the high NO, and then as a result high NO will be converted into NO2 quickly, and then as a result I will have the high NO2 concentration till things become stabilized and other things start taking up. NO2 becomes so much as that it is picked up by OH, so it is taken up, it's picked up by the ozone and things like that, and again both finally NO2 has to reduce, NO has to reduce, ozone has to stabilize as these are reducing, okay, stabilize, SCHO go down, because that reaction that we have seen, SCHO will continuously decrease. So you have the higher concentration of NO, that you can see the difference as to what can happen. So maybe your atmosphere is this, or maybe your atmosphere is something else, so you can model the things, of course in the limited context of the 4 pollutants that we are talking about. Take another example here. Here what we have done, increase more NO. Okay, that what happens? Okay, so we had that peak here. That peak is still building up. Okay, see here NO2 is going up. I have more NO. Okay, when NO was high, this was the NO2, and then start decreasing. This is like NO2. I increase more of NO. Okay, so then it is still increasing. This is NO2. Here NO was how much? 0.1, whatever the units, mostly the moles, and here NO was, tell me what is that? 1.0. That's good. So you see the difference that we are making here. ozone will be formed anyway, SCHO will come down. Okay, that's what SCHO will always be coming down and will always be oxidized. Okay, so see the model how the initial concentration can change, and the time scale probably should be the same, I guess. Time scale here it is a little bit more, but here time scale is same 120. Okay, here also time scale is 120 minutes, and then you can see here that photooxidation of formaldehyde is in a mixture of NO, NOx, and initial concentrations were this. Okay. Suppose, well, I hope I have it here. So quickly, the conversion of NO to NO2 is formation of ozone are therefore driven by SCHO. Okay, that we have seen. And its product HO2. Thus, the theoretical maximum ozone concentration could be produced by this system. Okay, SCHO initial concentration will be determined by this and this. Okay, when all the NOx is converted to HNO3, the system ceases to react. Okay, because that is the path that we are having. In a sense, a given system can be characterized by its ability to produce ozone. The effect of SCHO on NO2 dynamics is shown in the next figure, and that we will show you here. Oh well, you can't see it so much. Okay. This side is, I don't know how much, if you can see, this is NO2, and this side is your time, and this side is the concentration of SCHO. If you have, as you increase from 0.01, because earlier we had fixed the SCHO, right? So here you are increasing from this was 0.01, so you see some NOx being, NO2 being formed. You increase this, more NO2 is formed, you increase this much more, and you see the more NOx is more NO2, let me not call it NOx, more NO2 is formed. As the more NO2 is formed, then the more ozone is likely to be formed. Okay, so in a way we cannot undermine the role which hydrocarbons play, the role which SCHO plays, and this is of extremely important for us to do some control measures and to understand the complicacy of the system. And let me tell you, things are not so simple. Okay, it's just not, as I repeat again and again, the atmospheric chemistry is a subject in itself. You can be trained on this for the complete semester, but we will do it very, very briefly here. But that I'm very sure that you are getting a little feel that, well, why ozone is high and why things are increasing and why things are decreasing and things like that. And if you have to make some kind of impact onto the atmospheric control or control the ozone pollution, ozone is a serious pollutant, let me tell you again and again. So we also need to understand the hydrocarbons. Otherwise, hydrocarbons would also be governed by its own impact onto the human health. Okay, but then eventually you will see the control that needs to be done, whether this is to be done, which is the critical, it is the SCHO level which is critical, or the level of SCHO which is forming the ozone is critical. Okay, and that's how you decide even your air quality standards. Okay, so SCHO, for example, we have talked so much about the standards. For example, hydrocarbons. Okay, one is it's on, if I can use it, on TLV or that sort of thing. But this may be a concentration, let's say A, but this also has a potential to form the ozone, and that ozone concentration is to maintain this concentration, I need the concentration B. So my standard will be lower of A and B. Standard for hydrocarbon will be lower of A and B. You understood what I said? Okay. So that's what we use, all these things to say, okay, what should be the standard for hydrocarbon for that matter. So it's just not governed by its own harmful effects, okay, but it is also governed because it has the potential to form the ozone. Okay, and I want to fix a standard for ozone. So for this standard, what should be the B? Okay, and this for its own value, what should be the standard A? And then, well, choose out of these whichever is lower should become the standard for the hydrocarbon or for any pollutant which has a potential to form something else in the atmosphere. let's talk about methane. I know it is something similar, but it's not always that things are so this thing. More complications come as you have the higher compounds. We all are aware of that. Okay. It can methane, again we know the sources of methane and all. Generally methane doesn't come out from the cars and scooters and things like that, but we have enough sources of methane, and methane concentration is always significant. Not so harmful methane in the atmosphere, but and very stabilized compound. Methane, like is carbon monoxide, doesn't react anything, but it does react with what? OH. So OH can make everything react. That's the main and important part. So all the time we say OH radical, and so is again referring to the presentation given by the Ravi Khan Pathak. See, he was talking about OH radical all the time. Okay, same thing here. OH, it can be methyl radical. Okay, this is from the past, as we have done here. Again, this is from the past, but let's see what the methyl radical can do. It can react with oxygen, fine, and make CH3O2 radical, which is a methyl peroxy radical. Okay. So, and now we have to see what this methyl peroxy radical can do. Okay. So let's see what methyl peroxy radical can do, because the reason is, well, methane is in plenty, and this can also produce CH3O2 radical. There's a little dot that you see here, and then the chemistry of this methyl peroxy radical is so it is not only HO2 that we are referring again and again. There are many ways the NO could be oxidized, and the moment NO is oxidized to NO2, we have the two things that might go on, or two things we will go competitively, is the formation of ozone and formation of HNO3, right? Okay, NO2, the major routes for NO2 is either form the ozone and this thing. So in a way, I mean, we are answering the question that we raised, that why model failed. Model failed because we had not considered methane, formaldehyde, carbon monoxide, and then in a larger model we should consider all these things. Okay, and already you see the complexities that will come in the model with all the K's and things like that, and solving those equations with respect to time variability. Okay, how many of you understand the numerical modeling? Numerical modeling is one of the ways, or sometimes is the only ways to, you see, all of you know how to solve the ordinary equations, algebraic equation in terms of x, y, z and p, q, r, s. Like I have that many variables, and then I can write that many equations, and I can do this one. But what you can see from here, all these equations that you will see and that you will write, they will be in the differential form. They will be like the way we solve simultaneous equations, algebraic equations. Okay, in this process of the modeling, okay, I don't know how far we'll go in that. We will write many differential equations, right? And to solve these differential equations, okay, we don't have the ways and means to solve them completely. So we resolve to something called numerical methods. Okay, I'm not sure how far that will go into the numerical method in this course, probably not, but you should know that these equations are solved numerically. Maybe I might do some example for the numerical methods, but that's how you solve these equations, and then you can really show that the time functions and how the equation, how the reactions are changing up and down. And let me tell you, people have done the modeling, numerical modeling, with hundreds of equations going into your modeling process. How do you solve the, suppose I have a matrix of 50 by 50 algebraic equation, what is the method that you follow? Gauss elimination, very powerful method. So as you are solving the Gauss, using the Gauss elimination method, you can also write these equations, and you can numerically solve the equation for very small delta c and delta t, right? You can write delta c and delta t for every step, as a time step, and then you can put these numbers in Gauss elimination and solve it iteratively every time. That is how the numerical methods work. Okay. So these all equations are solved numerically generally and that takes a lot of computer time. Okay. The same thing we repeat here, competitive reaction, and now we are coming to something else. See, in the process there is also possibility. Okay. We are finding lots of HO2, but these HO2s can also combine to give me hydrogen peroxide. We do get a reasonably good amount of hydrogen peroxide. Okay. And what kind of species combined H2O2 is highly oxidizing, right? So you got something more which can oxidize something else, and in fact the oxidation of SO2 by not only the vanadium pentoxide by H2O2 is very significant. I don't know how much you know. When you want to measure the SO2 from the stack or in the atmosphere, you do it, take H2O2. Okay, this may be outlet. Put SO2 in there. This SO2, okay, will quickly, okay, make H2O4. Is it balanced? Should be balanced. And H2O4 you can do titration with standard alkali and can form what is the amount of sulfate, and once you know the amount of sulfate you can find out what was the SO2 concentration. In fact, this is the way. So you see how the atmosphere, okay, who can think of that H2O2 will be formed in the atmosphere and this H2O2 is formed. Okay, as if life is not simple, okay. HO2, that is hydroperoxide radical, which is very important for the formation of your NOx, can also react with this CH3O2 radical either with NO or with HO2. Okay, and then if it reacts with HO2, it produces acetic acid in the atmosphere. And these reactions all are feasible reactions. We are not talking something, oh well, let's try out something will be formed. No, they are formed. Okay, people can measure this, and you see, which we had not thought that it can even produce the acetic acid concentration. So don't forget that HO2 is just not oxidizing to NO2, oxidizing NO, but it can also react with CH3O2 radical to form the acetic acid. Okay, and then we are also producing H2O2 in between, which can take off some of the reactions in the atmosphere. Okay, it can oxidize many more things, but H2O2 is one thing. But of course, we are not talking the phase. This can happen largely this can happen in the vapor phase. SO2 may be in the vapor phase, but this H2O2 has to be in the liquid phase. Okay, it may be liquid phase, or this may be absorbed onto the particles, and the reaction can occur onto the particle surface and things like that. We will not get into those details, but of course certainly these are the topics for research. Okay, but we will stop here.